technologies starting from 130 nanometer till to 28 nanometer technology node, and he worked extensively in process development and device design, etc. So his current research interests are in the areas of carrier transport in highly scaled devices, indigenous technology development for space and defense applications, high voltage, high power devices, advanced semiconductor devices, semiconductor device modeling, computational lithography, and analog IC design. So now I request Professor Nihar to begin the session.
Thanks a lot, Anand, for the introduction. And let's begin technical session 2A, emerging technology. So before that, good afternoon to all of you. So we have around 5 papers. We have 5 papers in this session, and we'll start with paper 1, that is the instruction controlled in-memory sorting on memory star crossbars, and this will be presented by Sumant Paine of National Institute of Technology, Rourkela. So, Sumant, are you there? So, Anand, I think we should play the video now. So,
we'll play the video.
I am Sumant Paine from the Department of Computer Science and Engineering, National Institute of Technology, Rourkela. I will be presenting my work titled Instruction Control in Memory Sorting on Memory Star Crossbars. This is the outline of my talk. The first question which comes is why in-memory sorting?
Yes, I am there. Sir, yes, I am there.
Human architectures suffers a bottleneck for transferring data between memory and CPU. This degrades performance.
The video has started. Somehow it has started.
Data-intensive applications. In-memory computing can be an alternative approach to solve this problem. Sorting is an important data-intensive application where the big data, database and other applications require sorting. Sorting is a pre-processing step for many algorithms. Sorting within the memory will reduce fast transfers and cache misses. Memory star is being used as basic units for designing non-volatile memories. Memory stars can also be used to design logic circuits, which are called the memory star aided logic circuits. The memory star aided logic circuits allow in-memory computing. So the present work targets to use the memory star crossbars for doing the sorting in the memory using the memory star aided logic. Memory star was introduced in 1971. It is a two-terminal circuit and it is non-volatile. Its resistance changes from high to low and low to high depending on the direction of flow of current. It is compatible with the present CMOS technology. In 2008, HP Labs launched a titanium dioxide memory star, which has the property of changing of resistance. A single bit can be realized using a memory star, where its maximum resistance Roff is represented as logic 0, while its minimum resistance Ron is represented as logic 1, where Roff is larger than Ron. The memory stars can be used to design the resistive RAM, which is non-volatile, and also the memory star aided logic circuits. The memory star aided logic circuits, or the magic logic circuits, can be designed to realize any logic operations. The NOT and NOR logic memory star aided logic circuits can be installed within the memory crossbar. And this NOT and NOR, on the sequence of NOT and NOR logics, operations can be used to realize any in-memory computation, which is reconfigurable, and we also can achieve parallel computation using within the memory crossbar. The non-memory architectures can be realized using the memory star-aided logic circuits. The present work considers the magic-based architecture where the CPU is interfaced with the MMPU, but the CPU executes the program, whereas the MMPU, the memory star-based memory processing unit, processes the data within the memory. This avoids data transfer and reduces cache misses to improve performance and save power. 3 instructions M0, M0, and JSet are introduced for performing data processing within the MMPU. The M0 instruction performs a NOT operation within the memory. It takes 2 microoperations and 4 clock cycles. This instruction can be used for the copy operation within the memory. Similarly, the M0 operation can be extended for the M0 instruction. It also takes 2 microoperations and 4 cycles. The M0 instruction performs NOR operation on 2 input variables and can be used to realize any logic. The JSet instruction tells that if set then jump. If the bit of the variable x is high, then go to the branch address. X is a variable in the memory crossbar. This instruction takes 3 microoperations and 6 clock cycles and is used for the in-memory comparison operations. The in-memory sorting in this work consider 3 sorting algorithms. The 2 out of which the 2 selection and merge sort are the 2 comparison-based sorting algorithm, while the radix sort is considered here as a non-comparison-based sorting algorithm. All these 3 algorithms show similar best, average, and worst-case behaviors. The basic operations to perform the in-memory sorting are the comparison for the comparison-based sort. So this is the comparison for algorithm for comparing 2 m-bit numbers within the memory, where we use the JSet instructions and it takes order of m time. While for the swapping is a sequence of NOT operations. Similarly, a copy operation is also a sequence of 2 NOT operation, which the swap and copy takes constant amount of time. The in-memory selection sort has been implemented. Here you can see that it performs a selection sort on n elements within the memory, and the steps 2 to 18 finds the maximum element in each pass, while steps 3 to 15 performs the comparison operation, and steps 19 to 22 performs the swap operation, all within the memory. Similarly, the in-memory merge sort performs the merge sort operation within the memory, and where steps 3 to 19 performs the comparison, and steps 21 to 23 and 34 to 37 performs the copy operation. The in-memory radix sort is implemented for performing the radix sort within the memory. Each pass of this algorithm comprises of a counting sort on each digit, and each element in the array, input array, is considered as m bits, and each m bit is partitioned into delta digits, and each delta digits comprises of beta bits. Okay, so the steps 7 to 9 performs the counting in an array C, which is stored within the DRAM, and steps 11 to 13 performs the cumulative sum, as we've seen in the counting sort, and steps 14 to 20 and 21 to 24 performs copy operations, all within the memory. The experiments have been performed on the GM5 architecture simulator, where we have extended the ARM Cortex A75 architecture with the instruction set for the MMPU. The MacPad finds the power values of the CPU, bus, and DRAM for 32 nanometer technology. The MMPU power values are obtained from the current and the resistance values of the memristors during the micro operations. The CPU speed has been considered 1.2 gigahertz, and the supply voltage for the CPU is now 0.9 volt, while there are cache memories of L1 data and instruction caches of 64 KB each, and an L2 unified cache of 256 kilobyte. The MMPU has voltage for setting and reset voltage 1.5 volt, while the operation voltage of the gates is 1.0 volt, while the R on and R off are 1 kilo ohm and 300 kilo ohm respectively. The CPU and MPU are interfaced using a 44-line bus, where 2 lines are for the opcode of the MMPU instructions, 40 lines are for the address of the operands, and 2 control lines between the CPU and MMPU. The input size is varied from 10 cube to 10 to the power 12. Here is the comparison between the traditional and the in-memory sorting algorithms. For the selection sort, the in-memory sorting suffers loss of performance due to the order of m time comparison operation. The CPU-based sort is 18 to 31 times faster, while the MMPU-based sorting algorithm achieves a power saving from 40 to 78%. Similarly, the merge sort, the CPU-based merge sort is faster, while the MPU-based merge sort is having higher power savings due to no data transfer between the memory and the CPU. Here also, the comparison operation overhead degrades the performance of this the in-memory based sorting. In case of the static sort, there is no comparison. For a higher input size, the in-memory based sorting performs better and also achieves a considerable amount of power saving. There is an alternative approach to perform this in-memory sorting using the logic operations within the DRAM. We can use the method of activation, triple row activation, where the activation of 3 DRAM rows sharing the same sense amplifier can be done to realize AND operations within the DRAM, and also a minor change in the sense amplifier can lead to a not operations. So, but these are unreliable due to the value detection and destructive overrides. As we know, the DRAM needs a refresh, some energy for refreshment, and while the magic or the MPU-based system is reliable and energy efficient due to its non-volatile property, but still there are situations where both technologies can outperform each other depending on the particular logic which is being solved by their basic instructions. We can conclude here the in-memory sorting is performed on memory stack crossbar array with an architectural support with a new set of instructions. Higher power savings have been achieved due to reduction in cache miss and bus transfers. The time for comparing in-memory comparing degrades the performance of in-memory comparison sorting. In-memory direct sort performs better for larger input size. The requirement of low latency in memory. There is a requirement for the low latency in memory comparison for higher performance in memory comparison sorting and other comparison based operations within the memory. Thank you.
Thank you. So I think we can open up the question and answer session now. So I do not have access to the questions, so I'll get. So are there any questions? So this is a request to the administrator. If there are there any questions? Okay. All right. So, yeah.
I'll write in the.
Yeah. So, I have a couple of questions. So, Samantha, this is a very nice presentation. You're talking about memory store based circuits, but you have not mentioned what is the material and you means for your memory store. What is the material you're using?
The memory star material you am using actually is actually the platinum titanium dioxide platinum memory star. Actually, that model actually.
Okay, so you are using the model from where, or are you have developed your own model?
Plus, actually, there is some existing model is there. VTIM memory star model is there. I am using the VTIM memory star model.
Okay, so but how do you know that means? Okay, so means how do you know that this model that has been provided for this device it's very accurate, and have you checked that or?
Yes,
Or
actually there are some issues actually related to the memory star like sneak path current and all those. So which will create accuracy problem. So actually that's why I implemented a program control comparison. Means comparison can be done in our traditional hardware CMOS circuits using totally hardware comparator. Okay, so if I go for a hardware comparator, then there are some issues like sneak path, and those are which will create noise in the circuit. So to avoid that, I went to a totally software approach where I did a bitwise comparison using a small instruction set. So actually, there are problems if I want to design adders or incrementers within the memory. It creates there are some problems. Actually, we have to deal with that.
Mhm. So you also mentioned in your slide that your set reset time is around 1.5 volt, right? So from where did you get that, right? From the model, I mean, so your set the operation voltage, right? You are talking about that.
So actually, some relations are given, some equations are given in the model. Actually, you can for a given.
I'm talking about the voltage level, right? V set and V reset.
Yes, sir.
So what are the voltage levels?
Voltage levels actually so there's a relation, there's an equation actually for two input NOR gate, and there is a relation where the voltage level depends on the ratio of the R on and R off.
Okay.
On the basis of that I have written it.
Okay. And how did you how do you calculate power, right? So this is means I understand that you have used M5, but how do you calculate the power problem?
So actually the system is having two parts. Actually, the MPU and the CPU. So the CPU based power actually from the from the Gem5 we get the performance values, and we can use those performance values to the MacPad model, which is based on the CMOS technology. And for the memory star based logic, actually, whenever I'm keeping track, I've written a module for that, where whenever we are accessing the memory star circuits there by the instructions, so the flow of current through the memory stars due to application of different voltages are being tracked, and the changes of memory stick in the resistance. So those values I am using to calculate the power.
Okay. And you were telling that there is a significant power saving when you move to memory store based computing compared to CPU.
Yes, there is a possibility. Yes, there can it can be saved.
Okay, so there is a question from the audience. So, how is memory store more suitable for in-memory computation? So, how do you think is it because people are currently looking at a lot of other technology also, right? So, what is your view on memory store being a suitable candidate for in-memory computation?
So actually, if we compare with the DRAM technology, actually DRAM technology we have to keep there is some destruction of the value when it is accessed. So actually we have to refresh and we have to keep in mind the refresh logic, which is a very important part in DRAM technologies. But in case of memory star, since it is non-volatile, so if we can minimize the other some problems, some physical problems, then memory star can be a good candidate for the in-memory computing. And it can be also be very competent for the if we want to implement the neural networks also, we can it will be a very good component for them.
Okay, so when you're talking about this memory star, so you will use it in the cache memory, or means which level then, if you want to use it, or this is a standalone memory?
No, actually, memory star will be actually can be a replacement of the DRAM. DRAM is the primary memory which we have. It can be a replacement of it.
Okay. So the advantages that you are listed, right? So will it be valid for all in-memory architectures?
So actually, this is the advantage. So the disadvantage of this actually is that for every time I am accessing the memory star, actually, if I can do the whole computation without if the CPU can initiate once the computation and without having any exchanges of messages like passing the micro instruction, we can if the memory star works alone as a unit, then it will be much better. We can get a much better. Actually, if the program is taken within the set of instruction is taken within the memory star, it will be better. But actually, it is not so easy to do that.
Okay. Okay, thank you. So I do not have any more questions. So thanks for the nice presentation. So now we'll move to the next speaker. So our next paper in this session is in this session is a multiply accumulator for stochastic numbers without scaling errors. So this will be presented by Katsuhiro Ishikawa from Ritsumeikan University, Japan. And I think we could play the video now. So before we play the video, so please, it is a request to all the audience. If you have any questions, please post it here, and we'll ask this to the speaker. Okay, so you could play the next video now.
Thank you for the great opportunity to present our recent work in this conference. In this presentation, I would like to convince you that our proposed method is useful in stochastic computing. First, let me explain necessary basis for stochastic computing. Stochastic computing is an approximation calculation method which is a stochastic number which represents the rate of the ones in bit strings. Stochastic number in short SN is a bit string to represent a value by the probabilities of getting ones in bit strings. G3, X, Y, Z are SNs. G3 SN are 8 bits and 4 bits out of the 8 bits are ones. G3 SNs are different, but they are all represent 1/2. Next, I explain overview of the stochastic computing. We first convert conventional binary input number to SNs by SNG. Then we calculate our desired function by using SNs in SC manner. Finally, the real result of SC calculation is convert the conventional binary number by counting the number of ones in the result SN. X are expressed in stochastic number generator. SNG convert binary input numbers to stochastic numbers. SNG consists of a linear feedback shift register and a comparator. This output 1 when y is larger than x and 0 otherwise. Next, let me explain arithmetic operations in SC. The SN generated by SNG calculated by these SC calculators. I would like to introduce a multiplier and others as an example. This is a multiplier in SC. These input SNs represent 1/2 for both x and y. The SN output by the AND gate represents 1/4 in value. The answer is 1/4 by 1/2 and 1/2. From this, we can confirm that multiplication has been performed. This is other in SC. The SN output by the multiplexer represents 1/2 in value. The addition value should be 1, but the addition by SC's multiplexer is 1/2 scale addition like this. In conclusion, in SC 1 AND gate can perform the multiplication, and 1 multiplexer can perform the addition. Therefore, we can reduce the hardware cost by SC. However, there is a problem with the others in SC. The addition is SC by a multiplexer may produce an error depending on the value of the select line. You can see that two have the same SC value for the input x and y, but different value of the select line, the case are errors. In this way, one-half scale addition uses a multiplexer loses some information. Also, the output SN requires scaling, so the output result cannot use as an SN. And we may lose much more accuracy when we perform multiply accumulator operations for many numbers as shown in these figures. For here, I would like to introduce our proposed method. That multiplier accumulator operations was performed using an AND gate and multiplexer in the conventional method. We realize multiplier accumulator operations with high calculation accuracy by combining a special multiplier called SNMRO with the 3 others that we propose. Our proposed method does not use a multiplexer, and so we do not need scaling. First, I would like to introduction the SNMRO, that is special multiplier. One of the SNG is changed into down counter to reduce the hardware cost. I'd like to point out that required bits can be moved to the right, so the output bits can be reduced. Our idea is as follows. If there are multiple outputs of the SNMRO, we consider the addition can be realized by concatenating them like this. Necessary bits are only the first y bits of the output of AND gate. If we can collect all these necessary bits, we do not lose information. As an example, if there are SNs of 216, 116, 116, and if you collect them by the required y value like this, it will be 5/16, and we can confirm that addition is realized. we propose three methods to concatenate SNMRO of output. First, I would like to explain SO adder with shifter and OR gate. There are two SNMROs, and there are also two outputs. Only the first Y1 bits of the upper SN is necessary as explained. Therefore, here are the shifters that shift the lower SN by the value of the upper Y. After that, we add OR gate to connect the upper SN and the lower SN. This is an example. This Y1 bit, Y1 value of the SN is 4. The required shift amount is 4. This is the output that shifts the SN value by the shifter, and we collect these two SNs with the OR gate. When it is converted to 16 bits, it becomes 3/16, and so we can see that the product sum operation can be realized. By using a shifter and an OR gate instead of the multiplexer in this way, we can realize a multiply accumulate operation of SC without information loss and scaling. However, this method uses a shifter, which may increase hardware cost. Next, I would like to explain another method called XOR adder. This is a method that requires less hardware costs than the previous SO adder. This SO adder uses a shifter to shift the output to the lower SNMRO by the upper DC value. Like this, we add the value of the upper DC to the original input Y2 before we input to this XOR adder. After that, by using XOR gate, we can invert the value 1 to 0. For the first Y1 bit, and so we can shift the output without using shifter. Because this XOR adder does not use a shifter, the hardware cost may significantly reduce compared to the SO adder. However, because the XOR adder uses a binary adder for the input, the circuit area is still a concern. Thus, I would like to explain our third proposal called RDC adder. This is a method to reduce the hardware cost by eliminating the adder used at the input of the XOR adder. By referencing the value of the upper DC to the lower DC, we modify the lower DC so that the same function as XOR adder is realized. When the value of the upper DC is 1, the value of the input, the lower modified DC is not reduced. By using RDC adder, it is possible to further reduce the hardware costs compared to XOR adder. I have been explained our three proposed methods. Yeah, I show experimental result to analyze the calculation error and the hardware overhead of the proposed method. First, I would like to introduce the average relative errors. The blue line is for the conventional method, and the red line is for the proposal method. The wavelength is fixed to 1024 bits. The value of input here random select from 1 to 1024. The value of the weight randomly selected from 1 to 8. Please see graph. With a conventional method, the average relative errors increase proportionally as the number of input increases. On the other hand, the proposal method can reduce or increase the average relative errors. Next, I would like to show the average absolute errors. The setting is the same as the average relative errors. The blue line is for the conventional method, and the red line is for the proposal method. Please see this graph. For the conventional method, the average absolute errors are always constant. For the proposal method, the average absolute errors decrease as the number of input increases. As you can see, it can be confirmed that the proposal method is superior in terms of average relative errors and average absolute errors. Next, I would like to show the hardware cost. Please see the table. We comparing in the conventional method with the three proposal method. So other as NAND gate counts the conventional method. XOR adder can reduce NAND gate count a little bit compared to SO adders. However, we think this can be further reduced if the binary adder can be reused. RDC adder can be reduced to similar NAND count as a conventional method. In conclusion, RDC adder can reduce the hardware cost the most. However, XOR adder may further reduce the cost depending on how it is used. This is our conclusion. The presentation we propose a multiplex calculator in SC that suppresses information loss. As a result of the experiment, it was confirmed that the calculation accuracy is improved. Future work is investigate how effective this proposal method is actual applications. Thank you for your attention.
Okay, thank you for the nice presentation. So Dr. Ishikawa, so let me see if there are any questions from the audience. So Dr. Ishikawa, are you there? Yeah. Yeah. So I have not seen any question till late, but the questions may come. I'll ask you later. But I have few questions. So what do you mean by stochastic numbers? So yeah. So what do you mean by stochastic numbers?
Number, so stochastic number, stochastic number is a bit string to represent a value by the probability of getting what's in bit strings.
So could you give us some example?
Oh, hi.
Yeah, so could you please give me some example where the stochastic numbers are used? Yeah.
This example, SN, X represent one and half.
Okay. Yeah, the probability is half. So the probability is half of x for x, y, and z. So
Sorry, repeat please.
my point is what are the stochastic numbers and what is the application of them? Means where means you are talking about a multiply accumulator, and what is the application of this multiply accumulator where it can be used? So are you getting me? So where will you use this multiply accumulator? What is the application of this circuit?
For example, we can multiply two values used by only AND gate
Okay.
like this.
Okay. So what are different circuits to deal with stochastic numbers? When you are comparing your circuit with some reference.
Some device.
So okay.
Oh. そうです。はい、すいません。
So, oh, hello? Hello?
Yeah.
Can you hear me? Oh, my name is Shigeru Yamashita, who is the second author, so I'd like to explain instead of him.
Yeah, please.
So,
please.
yeah, so as you see here, the other in stochastic computing can be made by multiplexers, but here actually we lose many information by this way. So there is some calculation error in addition. But our proposal is maybe what is the page? What page がいいかな? Page number 9, for example.
Yeah.
So this is our idea that so when we calculate multiply accumulators, so we made multiplication. So as I mentioned, so we can multiply only one AND gate, but after that we need to add multiply. But here, actually, for example, if we multiply by 0.25, then, so for example, if we are using 16-bit or SLs, then quarter means we have only 1/4 in the lower SNs. So our idea is just the bits move to the first 4 bits. Then actually multiplication can be done only at the beginning of 4 bits. And so we compact the information into the 4 beginning bits. And then we can add like next page. So for example, if we want to add 4 multiple results, then just for example, we move the first multiplication to the first 4 bits red here, and next one is to the second blue one. Is that something like we saw in our case? We don't use simply multiply. MUX to add, but we move correctly, and then just concatenate. then we can add without any scaling errors. So that's our idea.
Okay. Yeah. Thank you. I got it. So if there are more questions, so I could ask at the end of the session because the questions are keep on coming. Okay. So thank you for the nice presentation. So in the so we'll move to the next presentation now. So so the next presentation. Okay, so we'll go to the next presentation. So the next presentation is minimization of switching activity of graphene-based circuits. So this will be presented by Dr. Subrata Das of Institute of Radio Physics and Electronics, University of Calcutta. So I request the administrators to start this new the next video. Yeah, could you please start the new video?
I am going to present our paper, Minimization of Switching Activity of Graphene-based Circuits. Authors are Subrata Das, Peter Pfizer, Soumya Pandit, and Devesh Kumar Das. This is the presentation outline. First, the introduction, then the discussion on graphene-based p-n junction, part distribution model of graphene-based p-n junction, followed by graphene-based gates and the estimation of switching activity, cascading of graphene-based gate, then the estimation of switching activity of graphene-based circuits, the rules and algorithms for switching activity reduction, followed by experimental result, conclusion and references. Now first the introduction. Graphene has several advantageous electrical properties such as high carrier mobility and saturation velocity. Graphene-based pass XNOR logic is an alternative logic style. In the subsequent slide, we will discuss this thing. Basic gates as well as circuit can be implemented with this type of logic. So in our research work, we basically implement the basic gates and circuit with the help of graphene p-n junction, and our goal is the reduction of the power dissipation. Now this circuit basically shows the graphene p-n junction, and it is constructed on a graphene sheet, and these two metal to graphene contact X and F are acting as the input and output respectively. E and H are the two back gates, and they are isolated from the graphene sheet by a thick layer of oxide. Here, if E and H are supplied with the same voltage level, then the two graphene region will have the same doping profile. As a result, a conducting path will be established from X to F. On the other hand, if E and H are supplied with different voltage level, then the doping profile will be different, and in that case, there will be no conduction path from X to F. So this basically represents the equivalent electrical model of this. Now come here. So just to mention that if we supply E and H with the same voltage level, then a conduction path will be established from X to F. So in the input side, if we supply high voltage, then if E and H have the same voltage level, then we have the output as 1. So this gate will basically behave as a pass XNOR logic, and we will take this concept of pass XNOR logic and we will implement other gates from here. Now we discuss the power distribution model. The physics of graphene is similar to that of CMOS. Now in CMOS circuit, power is mainly dissipated due to the switching activity and mainly due to the dynamic power loss, and this dynamic power loss mainly occurs due to the switching activity. Switching activity occurs due to the transition either from 1 to 0 or from 0 to 1. Now suppose if at node I, the number of ones is represented by Ni and number of zeros is represented by Xi, then the probability of occurrence of 1 at that node is basically given by ni plus xi, and the probability of occurrence of 0 is given by xi by ni plus xi, and hence the switching activity at that node is basically given by ni into xi by ni plus xi whole square. Now if we just consider simple OR gate, in the output of the OR gate we have 1 0 and 3 1s. That is why the probability of occurrence of 0 is 1 by 4 and the probability of occurrence of 1 is 3 by 4, and hence the switching activity at the output node of the OR gate is 3 by 16. Now we discuss the graphene based gate and the calculation of switching activity. So we already mentioned that if these two input E and H are supplied with the same voltage level, then this type of gate is basically acting as the XNOR gate. Now in the output of the XNOR, basically there are 2 1s and 2 zeros, hence the switching activities of the XNOR gate is basically 2 by 4 into 2 by 4 equal to 1 by 4. Now this is the graphene NOT gate. So here, if the input voltage A is 0, then only the conduction path will be established from input to output, and here at the input, if we give the high voltage, then if A is 0, then only we have the output as 1. So this gate will be acting as a NOT gate, and the switching activity of the NOT gate is 1 by 4. If here both A and B are supplied with high voltage, then only the conduction path will be established from the input to the output. Hence this will be acting as a AND gate, and here the switching activity occurs due to the switching at node Z1 as well as the node Z. Now in node Z the switching activity is 3 by 16, and in Z1 it is 1 by 4, and hence the total switching activity is 7 by 16. This is the graphene XOR gate, so it is XNOR gate followed by a NOT gate. This gives the XOR gate, and total switching activity is half. In case this is the graphene NOR gate, so in this case, if both the inputs are 0, then only the conduction path will be established from input to output. In the same, and the total switching activity here is 7 by 16. This is the graphene NAND gate. So if either A or B is 0, then the conduction path will be established from input to output. In this case, the switching is occurred at the node Z only. That is why the switching activity is 3 by 16. It is the graphene OR gate. So in this case also, if either A or B is 1, in that case, the path is established, and in this case, the switching is occurred at the node Z only. So switching activity is 3 by 16. In the similar way, it is the 3-input NAND gate, 3-input OR gate, 3-input AND gate. It is the 3-input NOR gate and 3-input NAND gate. Now this table shows the calculation of switching activity of 2-input and 3-input gates. Now we discuss the cascading of gate. Now for the implementation of large circuit, cascading of gates are required. Here we show just the cascading of AND gate, and the cascading is done in two different ways. The first one is known as the chain structure, and second one is known as the tree structure. But our consideration will be the reduction of the switching activity. Now we discuss the estimation of switching activity of any graphene based circuit. For this, we take a 4-variable function BC bar D plus BC whole bar plus A plus D whole bar, and we implement this function with graphene based circuit. So Z1 is basically C bar, so it is quite obvious that the switching activity at Z1 is 1 by 4. The switching activity at Z2 is also 1 by 4. Now Z3 is 4, 5, 12 and 13. It is the min term representation. So number of 1 is 4 and number of zeros are 12. Hence the switching activity at node Z3 is 4 into 12 by 16 into 16. So it is 3 by 16. In the similar way, switching activity can be estimated in each and every node, and total switching activity for this circuit is 1.574219. So with this approach, switching activity can be estimated accurately, but for the large circuit, this is a hard problem, and so this problem is not practically feasible. next model is the signal probability based method. So in this case, say for the example NOT gate, if the input probability is P, then the output probability will be 1 minus P and the switching activity is P into 1 minus P. For AND gate, if the input probabilities are P1 and P2, then the output probability at the final node is P1, P2 and the intermediate node it is P1. Hence the total switching activity is P1 into 1 minus P1 plus P1, P2 into 1 minus P1, P2. In this way, we can calculate the switching activity for all gates, and these probabilities are propagated, but this concept produce the total switching activity, not exactly, but it produces some approximate result due to the reconvergent path. So if we compute the switching activity for the given circuit, so in this case the total switching activity is 1.44763. It is some approximate result. Parker and Maglaski's method used to calculate the switching activity accurately, but this method is very time consuming, hence this method is also feasible for the practical implementation. Now in our paper, we modify the signal probability based method. In this method, we optimize the logic expression in each and every node. Say for example, if we consider this expression AB plus BC plus CA, though it is implemented in this format, but when we compute the switching activity, we will consider the optimized expression, and due to this optimization, the adverse effect of the reconvergent path will be reduced. Now the total switching activity of this expression or this circuit, basically actually it is 1.796875. Using signal probability based method it is 1.80, and using modified signal probability based method it is 1.795898. So though it gives approximate result, but it is very close to the actual one, and this will produce the result in the polynomial time. Now we discuss the rules for minimization of the switching activity. Here basically we transform the equation into logically equivalent but structurally different so that it will reduce the switching activity. Now if we use the cascading of gate, so in that case for AND gate and OR gate chain structure is preferable, for XOR gate T structure is preferable. If we apply this type of rules xy plus yz equal to y into x plus z, then this type of transformation will also reduce the switching activity. The application of the De Morgan's theorem, consensus theorem, this rule 5, rule 6 and the absorption rule will also reduce the switching activity. Now in this case, in rule 6, though the area is increased, but it will reduce the switching activity. Now the algorithm for reduction of switching activity. Basically in our algorithm we applied these rules when they are applicable to reduce the switching activity. Now the experimental result, in our experiment we use several benchmark circuit. First we optimize this circuit using conventional method, and the optimization for area was used. Then the proposed transformations are applied to this optimized circuit. We calculate the switching activity using conventional optimization method, and after applying our method, and both the switching activity and area are computed. This is the experimental result. The experimental result shows that switching activity either remains same or decrease in all the cases after applying the transformation. Area in most of the cases reduced, and sometimes it is increased, but the area into switching activity, this product remains same only one case, increase only one case, and for all the other cases this product is also reduced. Now the conclusion. So in this paper we discuss the graphene based implementation of basic gates and logic function, basically the circuits. The set of rules for reduce the switching activity is proposed. We use modified or improved signal probabilistic based method. Now the scope of the improvement is basically estimation of the switching activity considering the large circuit. Now these are some references. Thank you.
Okay. Thank you, Dr. Das. It was a nice presentation. Are there any questions? So, this is a request to the administrators. Are there any questions from the audience? Because I don't see questions in my chat box.
No, Nihar, there are no further questions.
Okay. So, basically, I have a few questions. So, when you're talking about chain structure and tree structure, right? So, I really could not get it. What do you mean by chain and tree? Right? In which cases you want to use chains and which cases you use tree structure?
Right, sir. So, say for example, we have a 2-input AND gate, and with this 2-input AND gate, we have to implement a 4-input AND gate. Now, suppose this can be implemented in two different ways. First, we take the 2-input AND gate AB, then CD, then take the output of the first AND gate, take the output of the second AND gate, and connect it to another AND gate. So, this is basically the tree structure. And in the second case, first we take the first AND gate AB, take the output of the first AND gate, and take the third input C, connect it to another AND gate, then take the output of the second AND gate and take the fourth output D, basically connect it to a third AND gate. That the construction in this way is basically the chain structure. Now in the chain structure, basically the delay will be increased since we take the one gate, after that we take another gate. In this way we propagate it. So in this case the delay will be increased, but the interesting thing is that in case of chain structure, the switching activity will be reduced. But in case of tree structure, though the delay is reduced, the delay is minimum basically. But in this case, the switching activity has some higher values. And in our case, as we want to minimize the switching activity, that is why we consider the chain structure for the AND or OR gate. But if we use the XOR gate, XOR gate, in that case, the tree structure is preferable for the minimization of switching activity.
Okay, very nice. So you have also calculated the switching probabilities. So you have a slide, I think slide number 9 or 10.
Right, sir. Right, sir.
So how did you calculate the switching probabilities, or you have taken it from some references?
Actually, taken from the references, but the way of calculation is that first, when the any input circuits, all the inputs are equally probable. So, say for example, if we take a 2-input AND gate, the input probability is both the cases are half, since the number of occurrence of 0 and the number of occurrence of 1 in the input side is the same. That is why they are same. Now, for the AND gate, from the logic of the probability, if we take the conjunction, then the two input probability P1 and P2, then the output probability should be P1 into P2. For the XOR, that is for the union operation, the output probability must be P1 plus P2 minus P1 P2. So basically, the concept of the union operation is taken for the XOR, for the OR, for the intersection operation taken for the AND gate, and in this way the probabilities are calculated. Now for a big circuit, we compute the probability at the output gate, and this probability is propagated to the next gate. In this way, we compute the probability.
Okay, got it. So, and also towards the end, you have shown the experimental result. What do you mean by experimental? It is still simulation, or you have actually done?
Exactly. So it is exactly not the experimental result. It's simulation result to more correct.
Okay. So when you talked about graphene-based circuit, so how this means in your overall presentation, where the graphene comes into picture? Because
right, sir. Graphene actually comes from
you have done the theoretical study, right? And it is valid for all kind of logic, means all kind of transistors, right? Or
actually, right, sir. Actually, so your question is why? Okay. So actually, this computation is same for all the circuits, but in case of CMOS circuit, the computation of switching activity basic formula is same, but in case of CMOS circuit, the computation of the switching activity is done at the output node only, and here we consider the switching activity at each and every transistor. And here the role of the just we take the basic concept of graphene gate, how the graphene gate is constructed, that thing is taken over here. After that, with that particular gate, how we compute the other gate and large gate and circuits also, and how we compute the switching activity and we minimize the switching activity. That is our work.
So has anybody already shown some experimental data means with the graphene transistors? So whatever you have done here, so are there any papers, means any group which has actually proven it experimentally? That's switching
Actually, sir, group from it is also my reference. They are working, but they are not computing the switching activities. They basically propose this kind of pass XOR logic, and with the help of pass XOR logic, they give some idea how to compute the gates. But here we take that idea and compute large gate and cascading of gates and the computation of switching activity, so that the power distribution is minimized. But in their research work, no computation of switching activity or no reduction of power distribution was discussed in that sense.
Mhm. Okay. So thank you, Das. I think we'll move to the.
Sir, actually, I'm not doctor. I'm just Subbuddha Das.
Yeah. Okay. Thank you, Subrata. And
Yes,
we'll now move to the next speaker. So our next presentation is optical waveguide channel routing with reduced bendless photonic integrated circuits. So it is very nice to see a photonics related presentation. So it will be presented by Mr. Sumit Sharma from IIT Roorkee. So Sumit, okay. So I think I request administrators to run this video, and then we'll interact with Sumit.
Yes. Sumit Sharma, research scholar in the Department of Computer Science and Engineering from IIT Roorkee, and I'm representing our work entitled Optical Waveguide Channel Routing with Reduced Bend Loss for Photonic Integrated Circuits. Here's the outline of the talk that includes a brief introduction about the topic with the already existing methods. Then the motivation and the proposed method will be discussed, and at the end, the comparative results of the proposed work with the already existing methods will be shown. Photonic integrated circuits are the integration of electronic and photonic circuits on a single chip, and in this figure, some of the benefits of photonic integrated circuits are shown that satisfy the increasing demand of higher speed, low power consumption, and low power dissipation in current VLSI circuits. Further, to design these bigger photonic circuits, an automatic photonic design process is required, as it is present in electronic design automation. In physical layout of optical circuits, an optimal routing of optical waveguide is very crucial and important step. And the routing of optical waveguide has these different type of losses, where the bend loss depend upon the angle and the radius of the bend arc, and propagation loss, it depend upon the length of the optical waveguide, and crossing loss is in the range of 0.16 to 0.2 dB per crossing. Here, from this table, we can see that the bend loss is decreased when the bend angle is increased. Hence, the waveguide having a smaller bend angle will have a higher bend loss. In the channel routing, a channel is represented as a horizontal path with the terminal list at the bottom and the top of its boundary. And here, it is the representation of our channel grid, where the waveguide follows a known Manhattan channel routing, and further the grid is divided into a number of cells, where a cell is represented here. It has a height of h and width of w, and here theta, alpha and phi, these are the angles along the cell. These are the existing work in channel routing that follows a diagonal or known Manhattan routing grid. And these are the channel routing parameters, where track sharing and track reduction, they reduces the total channel area, and bend reduction, it helps to reduce the total bend loss, and the horizontal restriction helps in elimination of smaller bend angle, which eventually reduces the total bend loss. In proposed work, we have used non-Manhattan routing grid, and all the four channel routing parameters are satisfied. The total signal loss depend upon the band loss, propagation loss, and crossing loss. And our aim is to minimize the total signal loss, which highly depend upon the total band loss, as the propagation loss and the crossing loss are significantly smaller than the band loss. And here, from this figure, we can see that an optical waveguide can move in 5 different directions from a given channel grid point. And this route shows this shows 5 different type of bands in our channel routing, where theta and alpha, these bands are smaller as compared to the remaining 3 bands. Hence, the theta and alpha, they will have a significant higher effect on the total band loss. And this is the problem formation of our work, where we route optical waveguide from unsorted bottom list to the top sorted list, having an objective of reducing the total band loss and reducing the total number of tracks inside the optical channel. Optical waveguide channel routing, OWCR, is the proposed work that follows a restricted horizontal routing. Without the restricted routing, a waveguide can route from vertical to horizontal and from horizontal to vertical. That results in a 90-degree bends. And here 90-degree is alpha bends. While in OWCR, whenever an optical waveguide has to move horizontally, it first takes a diagonal, then a horizontal, and from horizontal it moves diagonally. And this routing eliminates the presence of these alpha bends. And here, these are the different routing cases in the proposed work. First 2 cases, max is less than minimum, and there only one waveguide can be routed along a track. And if max position waveguide is far from the last index as compared to mean position waveguide from its start index, in that case, maxed position waveguide will be routed to the right hand side. Otherwise, mean position waveguide will be moving to the left hand side. And in the scenarios where max is greater than minimum, in such cases, the routing track is shared with the 2 optical waveguides, where the mean position waveguide will take a horizontal left and max position waveguide will take a right routing. And they'll route while following this horizontal restriction along the channel. So this is the example of the proposed OWCR. Here, these are the routing cases for all the intermediate passes, and this is the actual routing of optical waveguide along the channel grid. And in the result section, we see that there are total number of 7 tracks are used in this example. And due to the horizontal routing, there are no alpha and theta bends. And further, we varied the cell height h from 1 to 1.732, and we found that for a height of 1.732, the band loss is significantly reduced. And here we can see from the result that TBL for a height of 1 is 7.78 and TBL for a height of 1.732, and it is reduced to 6.25 dB. These are the simulation result of the existing algorithm. Here, the swap, there is only alpha plus theta type of angles, due to which the total band loss is smaller as compared to OWCR. However, it comes with an overhead of a high number of tracks, and we can see there are 10 tracks for swap, and however, OCR uses 7 number of tracks. In case of RBSS and LBSS, the total number of tracks are 9, and the total band loss is still higher as compared to OWCR. And this is due to the presence of alpha band along with the presence of this theta bands. Further, in case of OBSS and TNR, we can see that it is reduced the total number of tracks to 7, and even OWCR is using 7 number of tracks for this example. And further, there are no theta bends for both the cases. However, still the total bend loss for both of the cases is higher than the OWCR. This is because of the presence of alpha bends in OBSS and TNR. We have simulated our work for different test cases where the number of waveguides varied from 10 to 100. And here we have showed 3 different test cases with the number of waveguide as 10, 50 and 100 for test case 1, 5 and 10 respectively. And these results shows that the swap has least bend losses for all the test cases. So it is because the absence of the horizontal path along the tracks, which shows the presence of alpha plus theta bends in swap. And this absence of horizontal path increases the total number of tracks in swap, which eventually increases the total channel area. Now, OWCR gives a better reduction in bend loss as compared to the remaining existing work. And we can see from the test case 5 and 10, when the number of optical waveguides are greater than 10, in such scenario, OWCR has a less number of bend losses as compared to the remaining work. However, for the test case 1, where the number of optical waveguides are less than equal to 10, in such scenario, OWCR sometimes has a greater loss comparative to TNR. And this is why happening, because the TNR is having few number of twin bends as compared to OWCR. So here's the simulation results for number of tracks, and we have compared our test cases with respect to number of tracks for each and every cases. And here we see that OWCR has a less number of tracks as compared to swap, RBSS and LBSS in each and every case. However, OWCR has a higher number of tracks compared to OBSS and TNR. And this shows that there is a trade-off between TBL and number of tracks. These results are the comparative results of total signal loss, and we have shown total signal loss with respect to all the 3 different test cases. And here for test case 5 and 10, OWCR has less total signal loss as compared to these 4 work. However, for the test case 1, OWCR has slightly higher signal loss when compared to TNR. So this result shows that it verifies that the TSL highly depend upon the total bend loss among all the losses. So this is the conclusion of our work, where the proposed algorithm outperform over the state-of-the-art technique in terms of total bend loss. However, it comes with an overhead of increased number of tracks, and in future we are trying to find out an optimal solution that reduces both these number of tracks and total bend loss with varying the cell grid height. So these are the references of our work.
Thank you, Sumit, for the nice presentation. So I think the floor is open for some questions. So are there any questions? Question by the. You could hear me?
Yes, sir, I can hear you, but I'm not. There's no question in chat box.
Okay. So yeah. So I'll request administrator. So are there any questions?
No, there are no questions from the attendees.
All right. So Yeah, but so I have a few questions. So I think so. You are talking about bend loss, propagation loss, and the crossing loss, right? So
Yes.
because I mean here mostly you are talking about optical interconnects, right? But your integrated circuit is mostly your CMOS circuit, right? Or you are talking about optical interconnects, and backend is made of optical lines, right?
Yes, I'm talking about optical waveguides, optical interconnects.
Okay. So what is bend loss? But when you bend your waveguide by 90 degree, why there is a loss?
Actually, if we can see, there can be possibility of many bend, many different type of bends, but wherever there is a sharp bend in an optical waveguide, it will produce a lot of losses. As the bend loss, it depend upon the radius and the bend
Why
angle.
will there a loss when it bending? What is the physics behind this bending loss?
Yeah. Bending loss, it is directly proportional to the bend angle, and it is inversely proportional to the radius of the bend arc.
No, but
So
what is
wherever
the question, right? So I'm asking about the physics, right? Because I'm new to the photonics. So for me, I just want to
actually
know.
in this work we have I understood. In this work we have considered only the geometry part, but we haven't considered about the material and everything we haven't considered yet. So we are just taking the advantage of the geometry and applying it there in our channel routing to get the lesser signal loss.
So how do you calculate these losses through equations, or means you just count the how many bands are there, then you from your equations you count the losses, total loss.
Yeah, just from the equations which I have shown in presentation. So depending upon how many number of bends is there in each and every optical waveguide, so that will be the summation. After that, the summation of all these losses.
So you are also talking about the propagation loss of around 2 dB per centimeter. How much the propagation loss you are talking about?
Yeah, propagation loss actually it is coming very significantly smaller as compared to the bend loss. So that's why we are talking more about the bend losses compared to the propagation losses.
And crossing loss is also very low.
Yes, sir. Crossing loss we have considered as a constant. Uh,
Okay, constant. One crossing is so much loss, right? Okay.
yeah.
So which tool you have used for this?
Actually,
Your own tool?
we didn't use the tools. We are making our own heuristic algorithm. There is lack of tools because the device simulation is also going on, and in our presently we don't have any tool for the simulation of such circuits.
No, but you are talking about only the interconnect part, right? Waveguide. So can you do it some electromagnetic simulator or something where you could also see how much loss you have with different
Yeah, actually, that we can do, but till now we are able to just perform only a single device because being a computer science background, we are not able to perform for the bigger circuits how it will happen. Like there are many different components can be used where one resonator or interferometer. So till now we have done for device simulation for only one uh, interferometer, not the complete circuit.
Mhm. So but the number that you are taking for band loss. So from where did you get this number?
uh, Bend loss.
Yeah, let's
Yeah,
say
actually,
how
yeah,
many
we
bands are
have
there.
referred. Yeah.
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 From where you got
Uh,
this number that okay, this band loss will be this much for a 90
uh,
degree.
uh,
Yeah.
That thing we have taken from the work which the existing work which I am following. From there, we have taken these bend losses equations.
Okay. So yeah, I was just thinking how to verify that. Okay, this means whatever routing you are proposing is much better than proposed by other work, right? So and you, but when you're comparing with other works, right? You have done your own simulation with that routing, or you have just taken the numbers and you have compared to your routing
No. We have done our own simulation there.
with their routing.
Yeah, with their implementation.
All right. Okay, so I think I would like to thank you again for this presentation. So, in the interest of time, I will move to the next presentation. Yeah, thank you again.
Thank you.
Okay, so now we'll move to the last presentation of this session. And the presentation, the title of the presentation is Gain Stabilization Methodology for FinFET Amplifiers Considering Self-Heating Effect. And this will be presented by Sasank Banchor from IIT Roorkee. So Sasank, so you are available. Okay, so I'll request administrators to run this video.
Thank you for attending the online presentation of our work. The title of our paper is Gain Stabilization Methodology for FinFET Amplifiers Considering the Self-Heating Effect. The name of all authors and affiliation are listed here. Before giving you some facts and figures, I would like to give you some overview of our work. We are working in the analysis of various physical phenomena in FinFET devices and its implications on analog circuit. Since FinFET is an industry adopted and very popular device due to its excellent performance in comparison to the planar MOSFET. However, due to the confined structure and box layer within the active region, self-heating effect appears as a critical and important concern in these devices. Moreover, the gain instability due to the temperature variations has always been one of a critical concern in these devices in the analog circuit design. This issue becomes more complicated in FinFET amplifiers due to an additional temperature rise caused by the self-heating effect. So in this work, we have proposed a compensation technique to stabilize the gain against the temperature variations. We have demonstrated this technique for isothermal and self-heating conditions, and we have showed that the error in the gain can be effectively reduced by using the proposed technique. So this is the complete outline of our work. Since the technology scaling improves the device performance in terms of speed, power consumption, cost, etc., however, there are several challenges such as social effects, which also comes with the scaling. So there are several techniques to overcome these limits. Multi-gate devices, instant silicon, high-K insulators are some interesting alternatives, and FinFET is one of them. FinFET is a thin FinFET body wrapped by the gate. It can be either double gate device or tri-gate device based on the thickness of the top offset. So these are the advantages of FinFET device. It has better electrostatic gate controllability, reduced leakage current, improved short-chain effect immunity, etc. So now we will discuss about the self-heating effect. Self-heating effect is a critical issue in FinFET device due to its nanoscale dimension and confined structure, which resists to dissipate the heat from the active region. Here we have shown the thermal profile of a 14 nanometer SOI FinFET. This is the source region, this is the drain region, gate, source extension, and drain extension region. It can be seen that a hot spot appears at the drain extension and drain junction. Thus, the carrier velocity and threshold voltage reduces due to the additional temperature rise in the device. So the drive current also degrades, as can be seen in the output characteristics of the device. So the self-heating can lead to a serious device performance degradation and reliability problems. The gain instability with the temperature becomes more critical in FinFET-based analog circuit due to the self-heating and thus needs to be analyzed. Here we have shown the 3D schematic of a 14 nanometer SOI FinFET and the calibration of our simulation framework with the experimental data. Here we can see the doping profile of the of the channel and the extension region. It can be seen that a constant doping in the channel region, however a Gaussian doping in the extension region. The device dimensions of various device parameters are listed here. We have used the gate length of 20 nanometer, pin height of 26 nanometer, EOT of 0.85 nanometer, and these are the dopings and so on. So here we have shown the control plot of lattice temperature along the channel, and a hot spot can be observed at the junction of the drain extension and drain region. Here we have shown the profile of lattice temperature and carrier temperature and different region of the device. It can be observed that the peak of the lattice temperature exists in the junction of drain extension region and drain junction, while the peak of the carrier temperature exists in the edge of channel and drain extension region. So the position of hotspot is found to be located at the junction of drain extension region and drain region. Here we have shown the degradation in drive current at different gate voltages. Here we can observe that a higher current degradation at higher gate voltages, while it is negligible at 0.5 voltage and below that voltages. Here we have shown the power temperature curve at three different gate voltages, 0.4, 0.6 and 0.8 voltages. Here we can observe that the slope of the curve reduces by increasing the gate voltages. The slope of the curve is called the thermal resistance. So the thermal resistance reduces by increasing the gate voltages. It is mainly due to the increase in the head speed area. So the self-heating induces around 16% current degradation and 82 Kelvin temperature rise in the device at higher VGS, means at 0.8 voltages, and VDS when VDS is also 0.8 volt, while it is negligible for VGS less than 0.5 volt. Here we have shown the current degradation due to the self-heating effect. Here we have shown the output characteristics of the device at isothermal and self-heating conditions. Here we have shown the intrinsic gain at both the conditions. Since the self-heating degrades the drive current and the trans conductance, thus the intrinsic gain also reduces with the self-heating effect. Since the gain instability due to the temperature variation has always been one of the critical issues in the analog circuit design, this issue becomes more complicated in FinFET amplifiers as they have an additional temporary rise induced by the self-heating effect. Here we can see that the gain there are large error in the gain with the increase in the temperature. Here we have demonstrated the variation of the gain with the temperature for common source amplifier. We can observe that the variation in the gain with the temperature is almost a linear function. So a design methodology for FinFET amplifiers is essential to get a stable gain insensitive to the temperature variation. Here we have shown the behavior of gain with the supply voltage. We can observe that the gain increases with the supply voltages. So now we have two relationships of the gain with the temperature and supply voltage. One with the temperature and one with the supply voltages. So we can approximate both the relationship with a linear function. Here we can see that the gain decreases linearly with the rising temperature, and here we can see that the gain increases linearly with the supply voltages. So based on this relationship, we can estimate a compensation factor. Means if we are increasing the temperature, then we can increase the supply voltage by this factor, so that the gain will be stable with the temperature. So here we have demonstrated the compensation technique for isothermal and self-heating conditions. Here we can see that the gain there is a large error in the gain with the temperature without compensation, and here we can see that by using the compensation technique, error can be minimized. This is for the isothermal condition, and this is for the self-heating conditions. Here we can see that there is a large error in the gain, and it can be reduced by using the compensation technique. It is a compensation factor of 5.3 millivolt per Kelvin and 5.8 millivolt per Kelvin is found for isothermal and self-heating conditions respectively. It is reported that the error in the gain can be reduced from 17% to 1.2% for isothermal condition and 21% to 6% for self-heating condition by using the proposed compensation technique. Here we can see that the error in the gain by using the compensation technique is large in self-heating condition. Here it is 6%, here it is 1.2%. It is because to compensate the temperature variation, as we increase the supply voltage, then self-heating effect also increases. So in the self-heating condition, we can observe a higher error. So this is the conclusion of our work. In this work, we discussed the gain stabilization technique for FinFET amplifiers. The behavior of continuous increment of the gain with supply voltage is utilized to compensate the reduction of gain with the temperature variation. Since the self-heating is also a critical challenge in the device and circuit performance of FinFETs, thus the methodology for the self-heating condition is also discussed. Moreover, a method to determine the compensation factor is discussed to achieve a stable circuit performance. The proposed technique can be utilized in any FinFET amplifier to achieve a stable gain insensitive to the temperature variations. These are the references.
Okay, thank you, Sasank. Are there any? I don't see any questions. So administrators, are there any questions?
No question.
All right. So Sasank, so I have it's a very interesting presentation. So I have few questions. One point is you told that your self-heating means with self-heating your current is reducing, right? And current and GM everything will reduce. So this is mostly because of electron phonon interaction, or are there any other reason you are talking about?
Yeah, mainly because of carrier phonon scattering. Because we have considered both thermodynamic and hydrodynamic models in our simulation. So it is mainly because of the scattering phenomena.
Okay, so but it is interesting that your hotspot point and your peak temperature points are different, right?
Yes, sir.
So
Because,
why?
Because since the peak of the electron temperature is highest at the gate and channel in the drain extension edge, while the lattice temperature peak is at the near the drain extension and drain junction edge. Since the mainly heating is due to the carrier phonon scattering, and the maximum carrier energy is near the load part of extension region, but there is very less phonons. There is very less carrier. So mainly the carrier phonon scattering occurs near the drain extension and drain junction. That's why heating is highest at the edge of the drain extension and drain region.
And your self-heating is also scaling with voltage. You have shown right in one of the graph, right? So this power supply voltage. So what is the power supply voltage you have used in your simulations?
0.8 to 1 volts we have varied in our simulation.
And for when you are doing this common source amplifier, what is the power supply voltage across the transistor you have used?
Yeah, it was 0.8 volt, and to compensate the temperature gain here, we have increased it from 0.8 to 1 volt by some compensation factor according to.
So how are you doing compensating? That means you are increasing the voltage, the supply voltage, to have high current or
Yeah.
high gain.
Yes, by increasing the supply voltage, we can keep constant the gain with the temperature.
It will also increase power, right? Power dissipation. And how will you dynamically increase that voltage? Do you have thought of any circuits to dynamically increase that voltage when you see this self-heating?
Yes, sir. Actually, in literature, there are various circuits to compensate the gain, but the circuitry is very complex. Moreover, we have also one solution, JTC point, but that is also that is also not feasible because if we want to change our voice point, then this one will be not good. So it is better to compensate the gain. We can increase the power supply.
So my point was, have you thought of a circuit which will dynamically change the power supply based on the self-heating rate?
Yes, sir. In future work, we can do that. I think a feedback circuit can be used to some.
Mm-hmm. Okay, so I think it was a nice presentation, and thanks a lot for this. And also, I will thank all the presenters for presenting their papers in this session. So I only see 4 of them here. So I think now what is the next step?
No, so the next step is to thank you for a wonderful session, for coordinating it so wonderfully well. So on behalf of the organizers, let me thank you, Professor Mahapatra, for this session. And this takes care of the session. So we are finished with it. And then we will join tomorrow conference at 8 a.m.
Okay. So
Thank you, Professor Mahapatra.
Yeah, thanks for the invitation, and thank you. Anyway, I am a participant of this conference, so I'll also join tomorrow at 8.
I know. Yes.
Okay.
Okay, bye all of you.